Yes, so I think this talk does really follow up quite well the previous talk, and I will talk a little bit about mantle fluid upwelling. Yes, this work is kind of looking at early indicators of continental rifting from more geochemical perspective. So looking at the composition of fluids and hydrothermal springs, and how that can also form a basis of evidence when sort of answering these questions. So briefly, identifying these early stages of rift development can be challenging, as probably many of you are aware, and because often these areas are associated with sort of low seismic activity or aren't associated with sort of a volcanic activity. And so I'm going to explore how geochemical composition of fluids could be a useful indicator and add to sort of the evidence base for these questions. And one of the tracers that I'll talk about is helium, so isotopic composition of helium or presence of helium gas. And helium itself also is a resource. It is something that people are exploring for currently. So as well as sort of indicating presence of various tectonic regimes and rifting, helium itself can be something that we look for and explore for. And so these early rift environments potentially are also important for helium exploration. It could be this economic potential of these tectonic environments. And this is kind of a little bit where my work generally is focused on. So the location that I'll talk about is the extension of East African Rift. So it's slightly further north of where the previous talk is, but generally, if you can see my mouse, the East African Rift, I'm sure you're all aware, have these two sort of branches, the eastern and the western branch around the Tanzanian craton. And generally, in terms of hydrothermal fluids and volcanics, the northern part is older and much more developed. So we see a lot of volcanoes, and we see sort of these really well-developed hydrothermal systems with a lot of CO2 and these mantle signatures, sort of Lake Kivu and around there. And at the bottom of the Tanzanian craton is where we have these various provinces, such as Rukwa volcanic province, and kind of generally sort of more recent rift initiation areas. And this study is located to the southwest. So going southwest from the Tanzanian craton, sort of toward Central African Plateau, and in the Zambia region, there is this Kafuya Rift Basin where the study is focused. And so generally, this area, there are a lot of extensional faults and extensional features here going to the southwest. And so, yeah, here is where our sort of sample location is. So zooming in a little bit on that image here, the sort of yellow box, having a sort of closer look here, we have these fault zones. So they are kind of Neoproterozoic faults that potentially are reactivated currently. And the basement rock around here is very old. So it's kind of Archean to the Paleoproterozoic basement. And the area itself has low seismic activity, not really a lot of volcanic activity. So it isn't necessarily sort of apparent that rifting may be active there. But Mike Daly has published this paper in 2020, where from various geophysical evidence, they've suggested that in fact, this kind of southwestern extension from the Tanzanian craton to the southwest is seismically active, and it is an extension of East African Rift. And so some of the pieces of this evidence, for instance, are these sort of high resolution images of the relief, so kind of imaging these fault scarps that are really extensive, that can extend up to 100 kilometers along these faults. And without these kind of high resolution images, it would be very hard to detect, but we do see these kind of very sharp fault scarps and these features that are regional in scale rather than local. So based on the geophysical evidence, we've sort of also had a look into the geochemistry of fluids. And so if we look at this map on the right-hand side, the red dots here show locations of hydrothermal springs. So there are very many hydrothermal springs, hot springs in the area, and there has been very little work on studying them. So there haven't really been a lot of measurements. And we measured the composition of a few of these. So they're shown in these colorful circles and symbols. So there are some right within sort of the Kafue basin and kind of on the fault zone. And the samples are either geothermal wells, because there is a geothermal project going on there, or natural hot springs. And also we have these two kind of control samples further away from the rift zone. So one around 100 kilometers south and one to the north. And so they're called Lubungu and Mosali springs. So they're kind of what I refer to as basement springs, and these other samples are within the Kafue basin itself. So this is what the sampling locations kind of look like. They are these sort of hot surface expressions of hydrothermal fluids, and the sample collection involves sampling the gas phase itself. So they are bubbling with gas. You can see the bubbles, and you can collect the bubbles separately from the water and then measure kind of the gas composition and noble gas composition of these fluids. So looking at the helium isotopic evidence then for these fluids, helium is this tracer gas that we use often to differentiate fluid composition and fluid source from the crust or from the mantle. So helium-3 is sort of a primordial isotope of helium, and it is within the mantle. And it sort of fluxes through the mantle up to the crust. And so we know very well the helium-3-4 composition of the mantle. So helium-3-4 ratio, it is sort of a ratio of these isotopes, and it's normalized to the value of air. And so when mantle fluids are present, they are enriched in helium-3. So the mantle composition of helium-3-4 is about 8 relative to air, and then crustal composition of helium-3-4, which is much more enriched in helium-4, is around 0.02. So there is this kind of, on the y-axis, very big difference of compositions of helium that we can expect from the mantle versus from the crust. And so on this graph, I've plotted fluids from various locations in East African Rift that are kind of from various other studies that are better understood. And so we can see that, for instance, places like Lake Kivu, where it is a sort of really developed rift as volcanic eruptions, we have really high helium-3-4 ratios that are kind of mantle composition. And then as we go toward areas that are associated with kind of more younger rifting, we see this kind of trend going toward more crustal helium-3-4 ratios. And so the samples from the Kafue rift are here. So they're circled in yellow. And so we can see that samples within the basin have a helium-3-4 ratio of about 0.14. So they have mantle helium presence in them. There's a certain sort of helium-3 component that indicates that mantle fluids are present at the surface expression of these fluids. When we look at the composition of these springs that are further away from the fold, so there's the two springs to the north and south, they have just crustal composition, so they don't have any helium-3. Additionally, when we look at the carbon isotopes, so carbon isotopes of CO2 that is coming up with these fluids, we can also see that carbon isotope has a value of around 4, and that is a carbon isotope value associated again with mantle signature. So in summary, we have evidence, pretty unambiguous evidence, that mantle fluids are present within this fold zone. And where we are within the fold zone, we have sort of high helium-3-4 values, and further away from the fold zone, it's just crustal signatures. So that is mostly to do with the y-axis of this plot. Then if we look at the x-axis, helium concentrations, we actually see that these samples are associated with really high helium concentrations, so they're around 1 to 2%. And generally in helium exploration, this is considered really high. For instance, the composition generally of these gases is very similar to these gray triangles that are seen in the Rukwa Rift Basin in Tanzania. And you may be aware that there's sort of active helium exploration going on there. There's various companies developing helium fields. And actually, just today, we've seen an announcement from one of these companies that they have proved helium in the basin and flown 4.7% helium. So generally, these kind of early rift environments are associated with really high helium concentrations relative to kind of a more developed rift environments. Like that is important for kind of resource exploration as a side note. When we look at sort of the major gas composition of these fluids, all the fluids from the Kafue Rift are dominated by nitrogen and have sort of small CO2 component. And generally, that is, again, what we expect in this kind of early rift system. So this is a sort of a similar example of sort of a geothermal system from the Czech Republic. So here we have this graben, and kind of the composition of fluids is shown relative to the distance from the fault. So where we are right at the fault, we see that we have these really high helium free fall ratios that indicate a mantle source. And we have CO2, the gases mostly are composed of CO2, and there's very little nitrogen in them. And that is because CO2 mostly comes from mantle, and nitrogen is a crustal gas. And as we kind of go further away in distance from kind of the spreading center or from just the hydrothermal system center, we see that both the helium free fall ratios decrease, and our CO2 content decreases, and nitrogen increases. And so generally what we observe here in Zambia are these fluids that are dominated by nitrogen, have a little bit of CO2, and have slightly elevated helium-free 4 compositions, which is really similar to kind of around this sort of area on this graph, where we're just starting to see some mantle fluids, but predominantly they're still dominated by a crustal composition. And so generally then looking at how gases of hydrothermal fluids change with sort of development of a rift, this is a little summary sort of compilation of geochemical signatures of various parts of the East African rift and kind of how they change as the rift matures. So at sort of the earliest stages of rift initiation, we tend to have these nitrogen-rich gases that tend to have a lot of helium, so sort of high helium percentage, and most of it is coming from the crust. They tend to have very little CO2. And as the rifting develops and there's more mantle fluids present, the nitrogen gets diluted by CO2, so fluids become dominated by CO2. And there's much more mantle helium. So there's much more helium free, generally in terms of isotopic composition, but overall helium concentrations decrease, so they become very low. So from kind of a perspective of perhaps economic exploration of helium, these very, very early rift environments is where we can preserve sort of highest concentrations of helium, and they tend to be dominated by nitrogen rather than CO2. So in summary then, these sort of geochemical results that I presented, they present first evidence for mantle fluids within the Kafue fault zone in Zambia. And so these signatures are consistent with early rift initiation, where we have evidence of sort of mantle fluids at the surface. This supports active crustal extension that's been proposed from various other geophysical evidence of the southwest system, so southwest extension of the East African Rift. Okay, thank you.
Thank you very much. And thanks a lot for the very pedagogic slide for the people who don't know anything about geochemistry like me. It was really useful to see the evolution of the gas composition on the maturity of the rift. I really like it. Thanks. Do we have questions? Yeah, Fula.
Okay, really nice talk, Rūta. I really enjoyed that talk, and I remember seeing Mike's presentation on this some years ago at AGU on the preliminary, stages of the work. So really cool work. So my question, so as I was, listening to your talk, I remember that, the Rukwa Rift also showed so much helium degassing, and in the case of the Rukwa Rift, even though it's considered to be a magma gas, but in this case, we're in a very magma, or in fact, non-volcanic branch of the rift system. So what do you think about the depth of emplacement of magma? Because we see the volatile degassing, but there is no manifestation of magma at the surface yet. And I must confess that my postdoc has a paper just accepted in NatureCom and Earth and Environment, where we show that, blind magmatism can actually promote rifting. And I wonder if that is what we're having here. If we think about the relevance of, this volatile degassing to rifting, could it be a signature of emplacement of magma somewhere deep within the crust, or you think it's these volatiles are coming straight from the LAB to the surface?
Yeah, no, I do think there is essentially lithospheric thinning happening, and from kind of there's other geochemical studies, there seems to be evidence that along some of these faults, like lithosphere is thinner. But so yeah, I think there is magma emplacement into kind of the lower crust, but in terms of generally where kind of where it would be within the crust, and perhaps in the sort of question of if this rift is developing, at which point would we see volcanic kind of activity at the surface. I think it's kind of like a little bit hard to say. I don't know whether they always kind of behave in the same way, where there's a certain sort of stage of rifting where you're now expecting to see surface activity or not.
Thank you. That's fantastic. And congratulations on the work.
Thank you.